And this is the one that lands 40 meters away. The only thing that determines their time of flight is the height, because they have no vertical velocity when they're launched. So delta y equals 1/2 gt squared plus 0 times t. Right, that's the vertical equation of motion that you'd probably use here. It's all for t. If they have no vertical velocity, they're not going to have any difference in how long they're in the air. It says qualitatively compare the launch speeds for each rock. Well, the one that went twice as far was launched twice as fast. If they take the same amount of time to reach the ground and range equals Vx times t, then the one with twice the range must have had twice the velocity. Compare and contrast the vertical and horizontal components of each rock. All right, well, both rocks are going to land or hit the ground with the same vertical velocity. They're accelerated downwards for the same length of time, starting with the same vertical velocity. So when they reach the ground, the vertical velocity for each rock is going to be the same because their vertical information is still identical. However, the one that went twice as far has twice the horizontal velocity. So this is what the velocities would look like just before they reach the ground. The mass is a distractor here, just so you guys know. All right. Any follow-up there? I don't think there's any more questions on it. And all right, so this is number 11, or no, number 10. On linear, whatever, dynamics. There's a lot of ways to look at this problem. One of them is conservation momentum. Does the ball have any horizontal momentum before the collision? No. So does the ball have horizontal momentum after the collision? Yeah. So in order to conserve momentum, the ramp would have to have an equal and opposite momentum after the collision. So we know these two things are going to be separating after the collision. Now, that's not really speaking to the answer, but that's what's going to happen. Now, unfortunately, the ball also has a downwards momentum before the collision. That must be being absorbed by the table that this ramp is resting on. You know, probably because the table and the earth are pretty big, so you don't really see the recoil of the earth after this collision. However, if we want to just look at forces, we look right here where the ball would have hit the ramp. Consider the idea of impulse. In order for the ball's momentum to be, the downward momentum, to be stopped, there had to be a component of the force in that direction. Right, that had to stop the momentum of the ball going downwards. In addition to that, there had to be a component of that same force in this direction because the ball's accelerated to the right during the collision. This suggests there is a force from the ramp in that direction. Well, duh. Notice that the green arrow is perpendicular to the ramp. It's a normal force. The normal force from the ramp stopped the ball going downwards and accelerated it to the right, which means the ramp experienced an inverse and opposite force in that direction from the ball. It probably also experienced an upwards force from the table. That's a normal force as well, which means that the net force on the ramp had to be to the left, to accelerate it to the left. Questions about that? Is that pretty complete? Any follow-up? It does ask about the acceleration, so we should discuss the acceleration. It's hard to discuss the acceleration because we don't know the net force on the ramp. We don't really know the net force on the ball. But I do know ultimately that the component of the force on the ball in this direction has probably got to be equal to the component of the force on the ramp in that direction. That's Newton's third law. And in addition to that, the net force on the ball is equal to ma, and that net force acting on the ramp is equal to 2ma, suggesting that A2 and A1 are not the same. I'm thinking the acceleration on the ball is probably more than the acceleration on the ramp. In fact, I'd argue that the acceleration on the ball, the acceleration on the ball is probably twice the acceleration on the ramp. They experience the same size force, but the ramp being twice as big must accelerate less. The graph looks like this. It's got, velocity and time, 2, 4, 6, and this goes to 4, so looking at the graph, I don't know what the question's asked. Looking at the graph, and I didn't do a great job drawing it, but I don't really care. This is 2, this is 4, this is 6. So it goes from 0 to 4 meters per second in 2 seconds. That's an acceleration of 2 meters per second squared during this interval. Its velocity doesn't change in the next 2 seconds, so that's an acceleration of 0 here. And then in the last 2 seconds, it's an acceleration of negative 2 meters per second squared. Again, I don't know what the problem asks. I can just get that because I know the slope of a velocity graph is acceleration. I also know that the area under this curve has got to be the displacement. So the area here is 1/2 times 2 times 4, or 4 meters. The area here is 2 times 4, or 8 meters. And the area here is going to be 4 meters again, because I know it's the same size triangle as before, for a total displacement of 16 meters. Now, I don't know what the problem asks. I just know those things I can figure out just from looking at the graph. Now let's take a look at the questions. Number 16 says, calculate the average velocity and average acceleration from 0 to 4 seconds. All right, so if I want the average velocity, it's the total distance traveled divided by the total time. 16 meters divided by 6 seconds. That is the average velocity. Any question about that? All right. So, average accelerations, it says from 0 to 4 seconds. So you should have corrected me, because that is wrong. I did 0 to 6 seconds, and it wants from 0 to 4 seconds. So I got to cut it off right there. So from 0 to 4 seconds, the average velocity is 8 plus 4 is 12 meters in 4 seconds, or 3 meters per second. The average acceleration is the change in velocity over the change in time. The total change in velocity was 0 to 4 in 4 seconds, or 1 meter per second squared. They must ask one of these questions on the exam. I just don't know which one. Probably, maybe both. Not too hard though, is it? Question 17, notice what you asked, so let's at least get to your question. Calculate the net force acting on the object between 0 to 2 seconds, 2 to 4 seconds, and 4 to 6 seconds. Net force equals ma, and wants me to do it during the interval. I will need the mass. They give me the mass as being 3 kilograms. So from 0 to 2 seconds, the net force is going to be 3 times 2, or 6 newtons. From 2 to 4 seconds, the net force is going to be 3 times 0, or 0 newtons. And from 4 to 6 seconds, the net force is going to be 3 times negative 2, or negative 6 newtons. Ta-da! On the right side, this is mandatory. This has to be here, or there is no circular motion. So that sets the scale for the size. Now, the right side are the forces that can cause circular motion. Those are the two acting. One of them is going to be there regardless of what the object does. Even if it's not in circular motion, the ball will have weight. Suggesting that the force on the left can be bigger or equal to the weight, but can never be smaller than the weight. Do you guys follow that argument? I'll say it again. On the left side, the net force can be equal to the weight, because tension could be zero. But it can't be less than the weight, because there's nothing pulling up on the ball. So the smallest the force can be is mg, which means that the smallest the velocity can be is whatever the result of solving for it here is. Cancel the m's. That is the smallest the velocity can be for the object to travel through the top of a circular path. Whether it's going over the top of a hill or going over, this is it. Now, it can go faster than that because then the string could pull down on it some. But it can't go slower than this. If it goes slower than this, it doesn't travel in a circle. It starts to fall below that path because the acceleration is greater than the velocity carrying it forward. So like I said in class, you could just memorize that. But that adds to a number of things to memorize. But heck, you guys are in AP Psych. That's like 1,000 vocabulary words. I'm asking you to memorize like 4 things. Now you could figure this out, right? Put 0.7 and 10 in there. So the answer is square root of 7. Something, between 2 and 3. If you want a numerical answer. We've got this graph here, so let me kind of sketch it real quick. Look pretty good? Who cares? 3, 6. This is displacement in meters. And this is 10 newtons, so that's force. Alrighty. It says, a force that varies with distance, as shown on the graph below, acts on a 500-gram object that is free to move without friction on a horizontal track. How much work does this force do over the first 3 meters of displacement? So the first 3 meters is to here. Work done is going to be the area under the curve. It's the product. And that's because I have force and displacement here. I can't do this. Although I'm sure the answer 10 times 3 probably exists in the answer key. But that'd be wrong. And the reason is because the force was not 10 newtons for the entire 3 meters. The force started at 0 and increased as we moved. That's why you have to do the area under the curve. If you knew calculus, you could do the integration, but you don't know calculus, so we do it this way. Now that being said, the actual work done is going to be 1/2 base times height, or 15 joules of work is done. Question B is, what is the total increase in potential energy for the object over the interval shown? Now, here's where we could argue a little bit. The interval shown is 6 meters. So the total change in kinetic energy over the 6 meters is going to be 30 joules. It's twice as big, twice as much area. So if you look at the entire area, both of those triangles are the same. So there'd be 15 joules for this area and 15 joules for that area. And boy, is that Christmassy looking now, huh? Now, unfortunately, I think your answer key says it's 15 joules, which that's wrong. That would only be true if we're talking about the 3 meter interval from part A. I think the person who made your answer key is drunk or something. Let's go with drunk. It's more fun. But I didn't make the answer key, so I don't have to claim it. Questions about that? Because question C goes back to the 3 meter part. And we're going to need that information to answer question C, which says, if the object was moving at 1 meter per second, at the 0 meter mark, how fast is it moving after 3 meters? Well, the change in kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared. A lot of people get this one wrong because they forget about that initial velocity. This has to be 15 joules because they asked about the 3 meter portion, times 1/2 0.5, better convert that 500 grams into kilograms, times v final squared minus 1/2 times 0.5 times 1 squared. So I think that's going to be 59 equals v final squared. I'm just doing the math in my head, and I'm pretty sure of that. Am I right? Yeah, why not? You're not trying. So v final is going to be the square root of 59. Stupid numbers there. But okay, I'm pretty confident in my answer. I know math stuff. Can you guys even see the board with the door open? Yeah. All right, good. I don't have to see the board. I have a beautiful display right in front of me. First, number 16 is a bit outside our curriculum. I will say, in this problem, though, there are some things that you probably should know, even though it's not our curriculum. First, we have talked about the definition of power. It's right on your equation sheet. In your equation sheet, it's change in energy over change in time. But it's just any process that deals with energy over time. So it could be change in kinetic energy over time. It could be work over time. It could be change in potential energy over time. Any of these things are power. Anytime you change something's energy, the power required to do so will be the change in energy divided by the time. That's what power is all about. It's how fast you do work. So, efficiency, which is what this problem is about comparing either the work out with the work in, meaning how much usable energy do you get out of a system for how much energy you put into the system. You guys eat food, how much energy do you get? But because time would be the same in both of those, it's also power out compared with power in. So ratio, that's efficiency. Efficiency is how good are you at converting the energy from one type to something else. In this one, we're asked to figure out the power output compared to the power input to get efficiency. So it says, what is the output power of the engine? The output power is the fact that the car had a change in kinetic energy in 4.6 seconds. This is the output power. To get that change in kinetic energy, you're going to have to convert the 100 kilometers an hour into meters per second, which I believe is 27 point something. What is it? 0.8. So it's going to be 1/2 times 1,000 times 27.8 squared minus 0. That is the change in kinetic energy of the car, divided by how long it takes the car's energy to change, which I believe is 4.6 seconds. This will give you the output power in watts, which, as I recall, is a big number. 27 squared times 1,000. It's going to be a big number. Now, so 386,000 watts. It's the output power of the car. Now, it says, what is the efficiency as a percentage? The only way I can find that out is to know what the input power of the car is. The input power of the car is the fact that it burned gas, and it burned 1.76 times 10 to the 6 joules of chemical energy in 4.6 seconds. You'll have to figure out what that is. I don't know what that is, but it's probably much bigger than the other one. I mean, it's 10 to the 6th. You do have to convert it to joules, though, so you can be in the same units. That's why I converted it to joules. So how many watts is this? It's big. Nobody did it? I don't know. 369? There's a mistake then. I know what the mistake is. The mistake is right here. Hold on, let me grab the eraser. The mistake is right here. That's 386,000 divided by 4.6. It was never, we never divided by 4.6 there.
Well, no one else said anything, so because we just assumed that.
Whatever. Just tell me the answers here. What do you got? What's this one? The top one? 84,000 watts. And what's the bottom one? 300 and what thousand?
82
watts. So you divide those two, and that'll give you your efficiency. It looks like it's like 25% efficient. Maybe even less than that. Which, by the way, for a car, that's phenomenal. Cars are not efficient. Most of the energy is wasted. Human bodies, maybe just a little more than this. It's hard to get mechanical work out of a heat system, so most systems are not efficient. There are no 100% efficient systems. You can't get all the energy out when you're trying to convert heat to work. Anyways, next. Yes, sir. So in this problem, number 11, you're asked to lift the mass off the ground. So I've got a 50 kilogram mass that's going to be lifted upwards 10 meters. Well, the work done is going to become gravitational potential energy. How much energy will the box have when it's been lifted upwards 10 meters? Well, mgh, or 50 times 10 times 10, which I'm pretty sure is 5,000 joules of energy. So, how much power does it take to do so? Work divided by time, 5,000 divided by 10 seconds, will be 500 watts of power. Now, just so you know, you can't just go buy a 500 watt motor and hope that it'll lift things up. You can buy 500 watt motors that run little toy cars. They won't lift up a 500 Newton mass. They have to be able to apply enough force to do it too. So don't think power is everything. But if the lift were performed by a motor in the real world, how much energy would the motor consume? More than 5,000. It's the only answer you can give. More than 5,000. Justify, no systems are 100%, which means it will consume more energy than you will get in usable work. And we just had that conversation about, well, which systems are more efficient than the others. This is an electric motor. It's probably pretty efficient. Still probably not much more than maybe less than 50% probably. The efficiency is hard to gauge there, but you're not going to get that much. Let's make sure we understand the picture here. We've got four forces acting on the car. There's whatever's propelling the car forward, force from the engine, which looks to be 1,200 newtons. And then we have the force of friction, 400 newtons. We have the car's weight, which is 1,000 newtons. And a normal force, also 1,000 newtons. Good, the car's not, nice level road. In parentheses, I want to put 100 kilograms here. So we know. And actually, I think I got that wrong. It looks like it's 10,000 newtons. I just read it wrong. Old eyes. So it's 10,000 newtons upwards, 10,000 newtons downwards, which means the car is 1,000 kilograms. I know that because the car, its weight is mg. So they give me something's weight, I can get its mass by dividing by 10. So there, I've diagrammed the situation there. It then says, how much net work does the engine do on the car in the first 10 seconds of motion? So this is a crappy question. Well, crappy is the wrong word. It's a question that you will find confusing. You have a choice on how you want to do this. I'll tell you this. You're going to need to either figure out the change in kinetic energy, because that's one way to do net work, or you're going to have to go to the definition of net work, which is net force times displacement times the cosine of the angle. We have the net force acting on the car. That's given. It's 1,200 minus 400. That's the net force on the car. So I know, just from looking at the problem, that the net force is going to be 800 newtons. The problem is that force is acting for 10 seconds. So I don't know how far the car went. I just don't. Now, I could conceivably use net force times time equals change in momentum. Right? Impulse. This information there is about impulse. This would give me how fast the car's going. Of course, I could also use net force equals ma and find the acceleration. This would allow me to use a motion equation. From there, I could figure out how far the car goes or how fast it goes. Figuring out how fast it's going, that would help me with this whole change in kinetic energy thing. Figuring out how far it goes, that would help me figure out the work directly. Same amount of work either way. You pick which one you want to do. We have three options. Find the acceleration and use two different motion equations, or find the impulse. Which one? Acceleration? Great. Net force equals ma. It's 800 newtons equals 1,000 A. So A is going to be 0.8. So let's put here. A is 0.8 meters per second squared. T is 10 seconds. Now, initial velocity is 0. Do you want to use this relationship to figure out work? If so, we need the displacement. Or do you want to use this equation to figure out work? If so, we need final velocity. Pick one. Displacement or final velocity? All right, displacement. That's going to be delta x equals 1/2 a t squared plus vi times t. Or delta x equals 1/2 times 0.8 times 1 times 10 squared plus 0. Half of 0.8 is 0.4. 10 squared is 100, so 0.4 times 100 is 40. The car travels 40 meters. Now they know the car travels 40 meters. The work done will be the net force, 800 newtons, times the distance the car travels, 40 meters, times the cosine of 0 degrees. And that force is in the direction the car went. That looks to be 32,000 joules of work. It's a lot of work for a single multiple choice question. But it's not particularly hard work. I mean, I wouldn't lose other questions to get this one done, but it's achievable. The problem is I think people just won't do this amount of work. I think they'll get confused. It says, how much work does friction do on the car in the same time interval? That question isn't that challenging here. In fact, now that we know how far the car went, the frictional force is 400 newtons. It was given to us. So the work done by friction will be 400 newtons times 40 meters times the cosine of 180 degrees. This is going to be negative, and you'll get negative 16,000 joules of work. Yay. Next. So this problem, though, is a little harder. I have MV, and then I have this thing that's 9M just sitting there. After the collision, I have MV1 plus 9M V2. I don't know if it ricochets backwards, but they tell me it's an elastic collision, so it probably does. Our job is to figure out what it does. Now, this is going to be harder than what's on the test. If you know that MV plus 0 equals MV1 plus 9M V2, you are likely going to be able to solve the question that's on the test. I mean, if you know to do this, you will likely be able to solve the question on the test. Furthermore, if you know that in order to check to see if it's elastic, then you would check to see if the kinetic energy was equal. You're probably going to be fine for the test, because this is what our curriculum is really about. If it's an elastic collision, both of those have to be true. Now, I don't know what they ask on the test, but asking this question on the test is probably too long. But giving you one of these velocities and then asking if it's elastic, that's not too long. Either way, to solve this problem, the first thing I realized is I can cancel out all the m's. Mathematically, that's a good thing to do. And I can also cancel out all the 1/2 m's over here. This reduces my problem to V equals V1 plus 9V2 and V squared equals V1 squared plus 9V2 squared. The m's cancel out because our two masses are proportional to each other. They're proportional to m. Now, you might not realize it, but the unknowns are V1 and V2. The known is V. That was given to us. So we're trying to find V1 in terms of V. You could try to solve for it right here, but you'll be sorely disappointed because your answer doesn't just have V in it. It has V2 in it as well. So that's not the answer. To get the answer, you will have to substitute. You'll have to take this and place it down here for V1, because this will produce a single relationship that only has V and, in this case, V2 in it. If we solve this for V2, then we'll have V2 in terms of V. Meaning we had two equations with two unknowns. We had to eliminate one of the variables between them. Now, this is not easy. There's mathy math here that has to happen. And as soon as you guys start seeing mathy math, you know, you get all nerved out. So let's just look at this mathy math. It's a binomial square. Do you guys know how to do that? You're supposed to.
Yes.
You took Algebra 1. So first one squared. Multiply the two of them together and double it. And then it's the second one squared. That's good math. That math works. I noticed something right away. How convenient. So, add things. Factor things. Let's see. I can factor out a V2. I can factor out an 18. And I'll get a negative V plus 5 V2. Is that right? Yeah, that's right. I can still do math. You get two answers for V. I get 18 V2 equals 0, so V2 equals 0. And I get 5 V2 equals V, so V2 equals 1/5 V. Which one of those is right? Both of them. We asked the math to tell us the velocity of the second object. That's what this is. And if I look back at my picture, what was the velocity before the collision? The velocity was 0 before the collision. That's why I get 0 as one of my answers. Before the collision, it was 0. It's obvious. Unfortunately, I also get the second answer, that after the collision, this one had to be 1/5 V2. Now, that's not the whole thing. There's still more to go. I'll point out that right here, if I want to find out what V1 is, I got to put in 1/5 V there for V2. And then I can figure out what V1 is. V1 will be V minus 9/5 V, which is negative 4/5 V. Woohoo! There, we did the whole thing. Yippee, can you do that on a test? I don't know.